and welcome to my talk Optimizing for the Radeon RDNA Architecture. I'm Lou. I'm a delivery technology engineer at AMD. I joined a bit more than 2 years ago in November 2017, and since then I've been busy with helping developers to make sure their games run well on AMD hardware. So this includes a lot of optimizing work, and to do efficient optimizing, it's really important to know about the GPU architecture in detail. And there have been a lot of changes in AMD since last year in 2019, because we released actually a new GPU architecture. And so very exciting times. And this talk will give you an overview about this architecture and also talk about how to optimize specifically for this architecture. So before, we had the GCN architecture for about 8 years, if I'm correct, and since last year in July 2019 we released our first products based on a new architecture. It's called Radeon New Architecture, in short RDNA. These first products were the RX 5700 cards, and obviously since then we released a bunch of other products based on RDNA, not only desktop GPUs but also mobile GPUs. The next generation consoles will be based on RDNA. So you see a wide range of different types of products will be using this architecture. So this also means that one of our design focus was scalability. So scalability was very important for us when we designed this architecture. And then we also had special focus on geometry handling, on reducing cache flushes. So you should observe less cache flushes now. And also on the amount of working flight needed is now less to actually fill up the GPU with work. So what you usually want is that all units are busy when you are computing code on the GPU, and this should be now easier to achieve on RDNA. And we also had to focus on reducing the latency. So in the following, I will talk first about the architecture itself. I will give you an overview, compare the GCN architecture with the RDNA architecture, highlight the changes. So if you already know the GCN architecture, the transition should be for you fairly straightforward. If you don't know, there will be a quick recap. But yeah, so there are obviously many changes, but also similarities between these two. And then the second part of optimization, the bigger part, is the optimization part. So I will talk specifically about texture access patterns, about workload and data distributions, and then about some specific shader optimization. So we'll talk about a specific set of shader instructions. And yeah, first I will talk theoretically about these optimization strategies, and then also give an example of how these optimizations can be applied in a specific use case. First, let's start with the compute unit on the GCN architecture. So the compute unit is the heart of the GCN architecture, I would say, because this is the place where your shares actually get executed. So if you write code for the GPU, then this will end up more sooner or later on the compute unit, because they are the SIMD and Scala units. So a compute unit has in total 4 SIMD units, which are 16 byte. There's 1 Scala unit. Then also has some local data share, 1 level 0 cache, and so on. Then if you take 4 compute units, they share an instruction and a constant cache. So how does your code now get executed on the compute unit? So on GCN we have a fixed wavefront size of 64, but since one wavefront gets scheduled to a single SIMD unit, and the SIMD unit is 16 byte, this means we have a 4-cycle instruction issue scheme. So each instruction gets issued 4 times, and each time with 16 threads, so that at the end we have a total of 64 threads. So in this example, we first have an addition. This gets scheduled 4 times. So first the 16 threads, then the second 16 thread, and so on. And until we have issued all the 64 threads, we can move to the next instruction. In this example, it's the move instruction. Now let's look how this is realized on the RDNA architecture. So on RDNA we don't have compute units anymore, we have no workgroup processors, in short WGP. And if you look at the two pictures below, you see that they are kind of similar, but also at the same time not really. And let's look in detail about what the work group processor is. So work group processor still has 4 vector ALUs, but this time they are 32 wide. It has 4 scalar units. So on a GCN compute unit we had 1 scalar unit, now we have 4. And we still have local data share, of course. We have now 2 L0 caches, so they're not called L1 cache anymore, but L0, but conceptually they are exactly the same. Now, if you group 5 workgroup processors together, they share one level 1 cache. So, but this is not the same as the level 1 cache on GCN. As I said, the equivalent of the level 1 cache on GCN is the level 0 cache on RDNA. And you may also have noticed another difference here, because on a workgroup processor, each has its own instruction constant cache. So on GCN, 4 computers shared one, and on the workgroup processor, they have now their own. How does this now compare with the compute unit in general? So you can say that one compute unit is about half a workgroup processor, or in other words, one workgroup processor is equivalent to 2 compute units. And maybe you've heard the term dual compute unit before. This is exactly the reason, because one workgroup processor is about 2 compute units. You can also say a workgroup processor is a dual compute unit. It's just a different term. It means the same thing. So a dual compute unit is a workgroup processor. So don't confuse it. And it's because of exactly this reason that you can compare a workgroup processor with 2 compute units on the GCN architecture. So there's still a difference though, because a workgroup processor has actually the double amount of scalar units and also the double amount of instruction constant cache compared to 2 compute units. Now, how does the code get executed on a workgroup processor? The important thing to note here is that the wavefront size is not fixed on 64 anymore. Actually, it's now natively 32. So we have SIMDs, which are 32 wide, and we have wavefront sizes of 32 natively supported. This also means that we now have single cycle instruction. So the same example, first we have the addition, it gets issued once, and then we can immediately move to the next instruction, which in this case is the move instruction. And this one gets issued once as well. So with one instruction issue, we have immediately all the 32 threads of the wavefront. Then let's look at the bigger picture. So the GCN architecture first again. This example is the RX Vega 64. On Vega 64 we had 64 compute units. That's why it's called Vega 64. And then we also have a level 2 cache, it's 4 MB, and then a global memory based on HBM2. Let's look at the RDNA example. In this case is an RX 5700 XT. It has 20 workgroup processors, or also 40 compute units, like equivalent to 40 compute units more or less. And it has also an L2 cache, 4 MB. Global memory is now GDDR6. And the big difference here is that it also has an level 1 cache, which is shared by 5 workgroup processors. So this level 1 cache is new. There's no equivalent on GCN for it. It's just a complete new level of cache, which means in fact that there is more cache available on RDNA. So yeah, so you see on this level it's very similar between GCN and RDNA, just that we now have, instead of compute units, we have this workgroup processors, and very important here we have the level 1 cache, which is just a complete new level of cache. To summarize the changes between, like the most important changes I would say between GCN and RDNA is, first obviously we have the workgroup processors, which are also called dual compute units because they are equivalent more or less Then 2 compute units. So a worker processor has the double amount of scalar units and instruction concentration compared to 2 compute units, but otherwise it's more or less the same. Then we have one complete new level of cache, which is the level 1 cache on RDNA, and the equivalent to the level 1 cache on GCN is the level 0 cache on RDNA. We have now a wavefront size of 32 natively supported, but now here's the thing, RDNA also supports wavefront size of 64, so there are 2 modes possible. And what happens if the wavefront is of size 64? Then we have a dual issue of a wavefront of 32. So it's dual cycle instruction in this case. So the same example again, we first have the addition and then the move instruction. So if we are running wavefront of size 64, we issue the instructions twice. And on GCN it was always wavefront size of 64, but we issued the instructions 4 times. On RDNA it's natively supported 32, but we also support wavefront size of 64 via dual issue of wavefront size 32. This also means, on RDNA natively it's single cycle instruction, on GCN it's always 4 cycle instruction. Then a new thing which I haven't talked about at all yet, it's about geometry throughput. So on GCN we are always limited to 4 triangles per clock. This is by the primitive assembler, it's just a bottleneck, it's just the limit. And on RDNA actually we have the same limit, we are still limited to 4 triangles per clock at the primitive assembler level. But now this is only 4 triangles which are already counted, because what's happening is on RDNA that we have our triangles that come into the GPUs, go through the vertex shader, and then we have an automatic culling step. So you don't have to do anything with this is just automatically done by the GPU, and after the culling step they get fed to the primitive assembler. So this means that the triangles per clock weight submitted to the GPU itself, submitted to the vertex shader, can be higher than 4 triangles per clock. Then they get culled, and then the culled triangles, they are limited to 4 triangles per clock. So in GCN we didn't have this concept, so we are always limited by 4 triangles per clock. Doesn't matter if the triangles were culled or unculled. In RDNA it does make a difference, so the effective throughput you may observe can be higher than 4 triangles per clock. And for this you don't need to do anything, because there's an automatic step done by the GPU for you. Okay, now let's proceed to the second part of my talk, which is about optimizations. And in particular, I will talk about texture access. So first a quick overview about the caches and some topics that's changed about them, and then specifically about texture access patterns. Second talk will be about workload and data distributions. This year we'll talk about this weird thing that we now have wavefront size of 32, but sometimes also wavefront size of 64, which is a new concept. So on GCN was always wavefront size of 64. And then the last topic is about shade optimization. So I will talk about DPP and LDS permute instructions. So if you have no idea what this means, I will talk about this later. Okay, texture access. So first, let's talk about caches. As I already mentioned, on RDNA we have a complete new level of cache. It's the level 1 cache, and for you it just means you have more cache available on the GPU. Then, which was before called level 1 cache, is now called level 0 cache on RDNA. It's the cache directly on the worker processors, and on the worker processors we actually have 2 level 0 caches. And important to notice that these are not coherent. So if you look at the picture again below, you see you have 2 level 0 caches, and we have 4 SIMD32 units. So 2 of them are tied to one L0 cache, and the other 2 are tied to the other one, and they are basically always accessing one specific L0 cache. So this also means if you're exchanging data or accessing the same like memory of texture within the same wavefront, this doesn't have to bother you at all, because one single wavefront is at one SIMD unit, and this SIMD unit is accessing exactly one L0 cache. But if you're now running thread group of a larger size than 32, so you can have 2 wavefronts, for example, or even more, then these wavefronts might be distributed to different SIMD units, and these SIMD units could access those 2 different level 0 caches. And if you now basically accessing the same range of memory in the texture and modifying it and so on, then the 2 L0 caches could get out of sync because they are not coherent. And this means it needs to go one level up to the level 1 cache. And yeah, so it's just something, if you optimize for this, just to be aware of. Then other nice things to know is that the L2 cache has now more clients. This means that you should observe less cache flushes. So in particular, I'm talking here about the copy engine. The copy engine is now a client of level 2. Before it was not. Then the cache line size is increased to 128 bytes. So on GCN it was 64 bytes, on RDMA is now 128 bytes. So if you optimize for a cache line size of 64, then you may adjust this to 128, because this should still work good for 64, but now also for this 128, which is on RDMA. So it should be a win-win situation for you. Okay, now that was all about caches. So caches are very important when we access texture. And what we want to achieve is, if we load from textures, sample from them, is that we have a good cache hit rate and as few cache misses as possible. And this can be highly influenced by how we access this texture and what kind of pattern we use. So I'm talking here specifically about compute shaders, because in compute shaders you actually have explicit control about how your thread indices are arranged and so on. So natively, if you access the thread indices in the compute shader, they are arranged in a row major pattern. So it goes first along the x-axis, then along the y-axis, and if you also have third dimension, then along the z-axis. So it's row major. So now the thing is that textures are not laid out in a row major pattern. They are laid out according to the standards whistle. The standards whistle is well documented on Microsoft documentation about texture layouts. So if you go to the site, you will also see the information about the row major layout, about the standards whistle layout, and about a couple of other things. But yeah, the standards whistle layout is a layout which is sorted in a quad pattern. So if you look at 2 by 2 pixels, they are basically stored close together and so on. And this is how the texture is usually let out in memory, because this resembles a usual texture access pattern, which means that pixels which are close together are usually also read at the same time, so the probability is higher. So what we want is to load the texture as it's let out in memory, and this is according to the standards whistle. Which means for us that if we have our thread indices which are in row major layout, we want to transform them to be let out in a standard whistle layout, so which is this 2 by 2 quad whistle layout. So you don't need exactly the same layout, but the important thing is here that we have these 2 by 2 quad patterns. So, and recalculating the indices from row major to this quad pattern, you can think about it yourself how to do this, or you can just take this code and use it. So we basically figured it out already for you. So the input is the index in 1D, and it will give you out the 2D indices x and y. And then you can use these indices directly to index into your texture and load from them. Next, let's talk about workload and data distribution. Specifically, I will talk about this weird thing that on RDNA we have now a wavefront size of either 32 or 64. So first to notice that this is not something you as a developer can control. This is controlled by the driver, and the driver will basically decide if the shader will run in wavefront 32 mode or in wavefront 64 mode. And so you can't have an influence on it. This is based on heuristics, and the driver will try its best, what's possible. And so if you program your shaders, you shouldn't assume a fixed wavefront size. So the two different execution modes on wavefront 32 and wavefront 64 are shown in the slide again. So in wavefront size 32, it's natively supported, so each instruction is just issued a single time, because SIMD32 is natively supported. On wavefront size 64, each instruction is issued twice, because it's just via dual issue of this wave 32. So on wavefront 64, we have the lower and the upper part, and on wavefront 32, we just have this single instruction issue. Okay, so this leads us to the question, how should we design our shaders now? On GCN it was obvious, because on GCN we always had the wavefront size of 64. Now we don't know, right? So it's like no way to know, will this shader run in wavefront size 32 or 64, so what to do? The answer is quite simple. We should still design our shaders as if they would run in wavefront size 64. And yeah, this is amazing because 64 is a multiple of 32. This means it's still really well suited for wavefront of size 32, but obviously also for wavefront of size 64, and it will also run still well on GCN. So it's good for both wavefront size modes from RDNA and also good for GCN. Now the question is that all? Was it the whole message of this stuff? So no, obviously not. So if you look at the level, if you have your dispatch and then the amount of thread groups and how big your thread groups is, then yes, that's all. So just use a multiple of 64. But if you look inside a particular thread group, we can actually do more. So in GCN, that was it. But on RDNA, it's really important that you group your active and inactive threads together, because you can actually deactivate a larger group of threads if some conditions are met. So on GCN didn't care about it at all. RDNA does, and what I exactly mean with my cryptic words here, I will demonstrate in an example. So first, we recap again on GCN. We had a wavefront of size 64, and then we have the same example, first the addition and then the move instruction. So first we have 64 threads which are all active. So obviously we have to issue every instruction for all the threads. So on GCN it's 4 cycles per instruction, and we just have to issue them. Now, the example in the middle. Half of the threads are now inactive, but it's basically every second thread is inactive and the other threads are all active. So we still have to issue all the threads, so we have to go through all the 4 cycles. It's just how it worked. And the same is true for the last example. So in the last example, we also have half of the threads are inactive, other half of the threads is active, but now the first half is active and the second half is inactive. We still have to go through all 4 cycles for each instruction, because we can only skip an instruction if the complete wavefront is inactive. But as soon as one thread is active, we have to go through all the 4 cycles. That's just how it works on GCN. So we only benefit from it if all threads are inactive. As soon as one thread is active, we can't skip the instruction, so we don't benefit from this. Now let's look at RDNA. First, wavefront size 32. So we have the same examples. So first, all threads are active, so we have to issue all of them. Then the second example, only half of the threads are active, but every second thread is inactive. And the last example, the same number of threads is inactive, but now it's the last part of the threads which are inactive and the first part is active. So this first and last part is along a thread group of 64. So if you have a thread group of 64 but a wavefront of 32, this means we have two wavefronts because one wavefront has only 32 threads. So first, when all threads are active in this thread group, we run both wavefronts just as normally. Then the second example is just half of the threads are active, but it's every second thread, so this means that every wavefront actually has active and inactive threads, so we need to run both of them. In the last example, we also only have half of the threads active, the other half is inactive, but now since we grouped them together, this means that only the first wavefront actually has active threads and the second wavefront has complete inactive threads, so we can basically skip the instruction in case for the second thread, and we save some time. Now let's look if the wavefront size is actually 64. So for the first example, again, all threads are active, so we have to issue them all. Then we have the middle example, half of the threads are active, but just every second thread is inactive. And now since we are wavefront 64, we have first the lower part gets issued for the instruction, and then the upper part gets issued for the same instruction. So first the addition gets issued twice, and then we have the move instruction. So for the middle example, still we have to issue all threads because they are distributed in a way that we can't really skip anything here. Interesting is now the last example where we have also half of the threads inactive, but the first half of the whole wavefront is active and the second half is inactive. So this means the lower part here is active, the upper part is inactive. And the cool thing is on RDNA now, if either the complete lower part is inactive or the complete upper part is inactive, we can skip it. So in our example, the complete upper part is inactive, which means we can skip it and basically transform our wavefront 64 mode doing this shader execution temporarily to a wavefront 32 mode by just skipping the issue of the upper part. So we have the lower part, all 32 threads are active, we issue them, then we have the upper part, all 32 threads are inactive, we can just skip it and proceed immediately to the next instruction. And this is new, so in GCN we always had to go through all cycles per instruction as soon as one thread is active. On RDNA it's not true anymore. So if you have upper or lower parts which are completely inactive, or in case of wavefront 32 this would mean still a complete wavefront, then we actually can save some time. So as a conclusion, use still a module of 64 as thread group size. This runs well in both modes for RDNA, and it also runs well on GCN. And if you look inside a single thread group, try to group your active and inactive threads together, because you can skip parts of the wavefront if you're running wavefront 64, or if you're on wavefront 32, you can skip just the wavefront. The last topic about optimization is about shader optimizations. And in particular, I will talk about how to exchange data between threads. So if you look at threads in general, we can always use global memory to exchange data between them because every thread has access to this global memory. Obviously, global memory is really slow. If you want to exchange data only between a single thread group, we can use local data share instead of global memory. Local data share is way faster, and I really recommend you to use local data share if you can. Now we can even go one step further down if you only look at threads within a single wavefront. Because if we have threads within a single wavefront are exchanging data, we can use DPP or LDS permute instructions. So first of all, DPP and LDS permute instructions, they are nothing new in RDNA. So if you use them, this will also work on GCN because they are already there. There are some specifics have changed. I will talk about the RDNA specifics you should be aware of to actually use them in an efficient way. But just as a general reminder, if you use them, it will also work on your older generation cards. So now, first, let's clarify what are DPP and LDS permute instructions. So DPP stands for data parallel processing, and LDS permute, why is then LDS if it's not really LDS? So first, let's talk about DPP, about data parallel processing. So as I said, we are talking about exchanging data between threads within a single wavefront. So we have our wavefront, now it's size 32, and each wavefront is residing on a single SIMD unit, so they're also accessing the same registers. So in this example, the threads within this wavefront have stored the individual values in a vector register. In this example, it's V0. So for example, thread 1 stores the value 8 in V0, and thread 0 stores the value 1 in V0. And now we can use DPP that those two threads are actually exchanging their values, which means that thread 0 now reads the value 8 and thread 1 reads the value 1. And this is just directly, so they are accessing the register directly, so register access is really fast, and we don't need to use any LDS or global memory even. And that's the concept of DPP. So just basically using the registers themselves to exchange the data between the threads. So for DPP, there are two different modes. So the first mode is using DPP along a group of 8 threads. So if you just swizzle data in like a smaller group, a group of 8, you can arbitrarily swizzle them. So basically you can let thread 8 read any value you want within this group of 8. The same holds for thread 1, thread 2, and so on. So you can swizzle them however you like, and this will be very performant. The second mode is DPP 16. So in DPP 16 we have a predefined set of swizzles. These are permute of 4 threads, row shift left, row shift right, rotate right, then mirror the threads within half, so basically within 8 threads, and then the other 8 threads, or mirror across the whole group of 16 threads. So this is the predefined set. So, which means if you use DPP within a group of 16 threads, and you can use this predefined set of swizzles, and it's also very performant, but maybe you need to use a combination of them. And then you need more instructions. So what now if you are using swizzles along a bigger group, along a group of 32 threads? In this case, you can use LDS permute. LDS permute is using LDS hardware. Yes, that's why the name comes from, but it's not storing and loading from LDS memory. So it's just using the hardware to calculate the correct address, but that's all. But it's not storing and loading to LDS memory. It's still using the register. So how does it work? We have the register V0, still the same example. Then it's storing the data in a temporary buffer, which is still on register level. And then the next step is it's reading from this temporary buffer. So this means it's using additional VGPS, and you need like more steps. It's using LDS hardware to calculate the correct address, but it's not loading storing to this LDS memory because it's using this temporary buffer within the register space, so it's still very efficient. So now general guidelines when you want to use DPP in LDSP mode. As I said, there are two DPP modes. One is DPP 8 and DPP 16, which also means that DPP is limited to a group of 16. And as if you're running DPP 8, the Swizzles are arbitrary. This means that if you want to ensure best performance, then you should stick your Swizzles within a group of 8, because this will be always just can be issued within one instruction. If you are getting wider, if you are doing Swizzles along a group of 16, for example, maybe it's very efficient as well, depending on your Swizzle pattern, but sometimes you need more instructions to actually realize this. And then, of course, don't go beyond a group of 32, because in this case you can't use DPP, you can't use LDSP anymore, so the compiler needs to use some other techniques, and this gets really quickly really ugly. So when I tried this to do Swizzles along a group of 64, in case of wavefront 64, obviously this is also not a problem here, then it was using a lot of if and else branches, it used read first line, and yeah, just don't use it. If you do Swizzles, stick to a group of 32. If you go beyond this, then use LDS or something else, but don't do the Swizzles. So now I was always talking about you should use DPP, you can use DPP, you can use LDSP mode and so on, but obviously on the high level shading language, so HLSL or GSL, there is no DPP or LDSP mode instruction, right? So how to do this? So if you want to use these instructions, you have to use wave operations or subgroup operations, and if you follow the previous guidelines, they can get translated into DPP and LDSP mode instructions on the ISR level, and they actually will, if you follow the guidelines, and if you have like some Swizzles within a group of 8, then the compiler will notice this and will do the most performant way, which will be most likely the DPP usage. So let's go to a concrete example. So let's Swizzle within a quad actually. So we have quads and we want to exchange the data between the quads. So quad means we have 4 consecutive threads. So for example, thread within the 0, 1, 2, 3 is one quad, and we want to exchange the data between this one quad. So there are specific instructions for this. So in shader model 6, it's the quad read across X, Y, and diagonal, and in GSL, it's the subgroup operation with subgroup quad swap horizontal, subgroup quad swap vertical, and subgroup quad swap diagonal. So here first the horizontal swap, which means that thread 0 exchanges its data with thread 1, and thread 2 exchanges its data with thread 3. Then the vertical swap, so thread 0 exchanges the data with thread 2, and so on. And lastly, the diagonal swap, where thread 0 exchanges its data with thread 3. So if you now look at a code example, now this is also using GLSL. So what we want is that we actually want to sum the individual values within the quad together, so that at the end each thread has the sum. So we first add the 2 horizontal ones together, then the vertical ones and the diagonal ones. And if you see how this translates into ISA code, we actually have our addition with the suffix of DPP, which means that the first addition is basically adding the value of thread 0 with the value of thread 1, and also the same, the value of thread 2 with the value of thread 3. So if you look at the quad perm Swizzle pattern, you see here you can directly see the horizontal quad Swizzle. Then in the second instruction you can see the vertical Swizzle, and in the last instruction you see the diagonal Swizzle. And yeah, you add them directly, so it's one instruction for the addition and the Swizzle actually. So as you see, this is really performant. This is how DPP works. And yeah, at the end we have the sum in each of the threads, which is in this example 13. So now I talked a lot about optimizations in theory. Let's look how we can actually apply these optimizations in a specific use case. The use case here will be the case study of a downsampler. So first, about downsampler in general, what is usually done, so it's a very common approach, is that if you want to generate the MIP levels of a given texture, that each MIP level gets generated in a separate pixel shader pass. So this means one MIP per pass. And these passes are divided by barriers, because before we can compute the next MIP, we have to be sure that the previous MIP is already computed, because this next MIP depends on the previous MIP. That's why we need the barrier in there. Then the other thing you may have noticed that for the lower MIPs, so if you go really down the chain, so MIP of size 16 by 16, 8 by 8, 4 by 8, 2 by 16 by 16, 4 by 16 by 16, 8 by 8, 4 by 4, 2 by 2, and 1 by 1. You see that it's really small sizes, really small resolutions. We don't have many values to compute. We don't need a lot of threads to do this job, but we still need to wait that the previous MIP is finished before we can start the next one. So that means we have very few working threads. Most of the GPU is just waiting for these few threads to finish the work. So we have really low occupancy, and yeah, this is not efficient at all. And you see it in this RGP capture that the occupancy of the lower MIPs is really, really low, and the GPU is basically just idle and is just waiting for these few threads to finish. And the question is, can we do better? So this problem tries to solve our single pass downsampler, GPU Fidelity FX single pass downsampler, in short SPD. And SPD idea is to compute all the MIPs within a single compute shader pass. So the basic concept is that we have a thread group of size 256. Each thread group computes a patch of the complete source texture, a patch of size 64 times 64, its downsample is to 1, and then the last active thread group does another round of downsampling. So in total, we can downsample a source texture of size 4096 squared down to 1, so computing 12 MIPS levels. So here we see again, so we have the source texture, then we have the patches of size 64 times 64. Each patch gets downsampled individually by a single thread group down to 1. Then we have to wait until all thread groups are done. So this is a global synchronization point. It's the only global synchronization point we have in this whole approach. And once all are done, then the last active thread group can continue. So we use the last active thread group because then we know all other thread groups are done with its work. And the last active one can do another round of downsampling and compute the last few MIPs. So if you look at the RGP capture of this approach, you'll notice obviously it's just one single pass. We don't have barriers in between anymore. The end part where we really have low occupancy is greatly reduced. So this small tiny part is about, I think, 2% of the whole pass. This is where the last active thread group is computing the remaining 6 MIP, and you see it's really, really short, but we don't have these barriers in between anymore, which is like making it considerably long. It's just really a small part of the whole computation pass. And yeah, since we don't have the barriers anymore, we can do pipelining on the same queue. So we just issue the next pass, which needs to be independent of this downsampling, obviously, but we can just issue it basically afterwards, and then it can overlap. So we don't have barriers within the downsampling chain, which is preventing this. And of course, you still can put it on the async queue. This always works as well. So let's use this SPD approach and see how the previous optimization strategies were applied to SBT to get the maximum performance out of it. First, let's talk again about texture access. Texture access is really important for SBT in general because loading from the source texture takes a big part of the time, especially if you have high resolution textures, so it's a lot of data to load, and this is a bottleneck of this approach in general, just loading from this texture and waiting until this data is available. So getting this as fast as possible is very critical, as I said, especially for high resolution textures where we will go out of cache. Doesn't matter what we do, so we have to be sure that we use the cache as efficiently as possible. Again, let's recap. So if we issue a compute chainer, the thread indices are laid out in a way major pattern. So what we usually see is a thread group of size 8 by 8, and then the indices which come from the threads are directly used in accessing the texture. So in case of SBT, we have a thread group size of actually 256, 1, so it's in 1D, but we can easily remap them in 2D. So this would be a 16 by 16, and then we still have this row major pattern. So now we can use this pattern to load the texture. So it's 16 by 16, the threads. In the beginning, I said each thread group is downsampling a patch of 64 by 64. This means that each thread needs to load 16 values, either by 16 load instructions or 4 sample instructions with a bilinear filter. In the following, I will always assume that we are using a sample instruction with a bilinear filter, so we have 4 sample instructions used to downsample 4 quads. So we have 4 2x2 quads which are downsampled to 1 output value using a single sample instructions. So 4 sample instructions per thread, and we can arrange them differently. So in the following, when I compare the different texture access patterns, we have to first compare how the threads are arranged. So in the first example, they're arranged in a row major pattern, and then how the pixels are arranged within a single thread. So in this example, they are actually scattered. So as I said, each thread is loading 4 2x2 quads, and these single 4 2x2 quads are scattered around in this example. They are scattered in a way that if you look at the single sample instructions, all the pixels loaded by the complete thread group are close together. So you see also in this example here, there are 256 threads, this is the whole thread group, and I colored them according in groups of 64, assuming a wavegroup size of 64. Of course, we don't know if it's a wavegroup of 64, it could be also 32, but conceptually it's the same. And it just shows here 64 because it's better to see and there's not so much clutter in the picture. But just to be sure, the conceptually it's exactly the same as you would further group them to 32 threads. So, but here it's important to notice, if you look at the whole thread group and all threads within this whole thread group, they're arranged in like 16 by 16 in this row major way. Then if you look at the single sample instruction, they load a complete block of 32 by 32 threads, because each thread is loading a quad of 2 by 2, and then once this first sample instruction is issued, then we move to the second sample instruction, so we're loading the next 32 by 32 block of pixels from this texture. So how can we evaluate this strategy? First, of course, we can measure the performance. I will go to performance later, but then there are also some other things to notice further. One thing is that, so we load from the source texture, compute the output from MIP1 using the bilinear filter, and then we have the question how to compute the values for MIP2. And in this case, because we have a row major pattern for our thread indices, we have to use local data share. We can't use, for example, quad swizzle, because the threads are not arranged in a quad but in a row major pattern, so they're forming a lane and not a 2x2 quad, which is needed if we want to use a quad swizzle. So this is just something to notice. We can't use quad swizzle, which could be a further performance improvement. Maybe not, so at this stage we don't know yet. I will talk about this later, but if you're using this texture access pattern, it's not even possible to try it out. So now let's look at a different texture access pattern. So we still have row major in the thread indices, but now the 4 2x2 quads within a single thread are now grouped together. So before they were scattered around, now we group them together so that each thread actually directly loads values which are close by. But on the other hand, if you look at the single sample instructions, at the pixels which are loaded by all the threads within the thread group, then these data values, these pixels, will be actually scattered if you look at the single sample instructions. And before they were close together, but the values were scattered around the threads. And now it's basically different. So the single sample instruction is loading scattered values, but if you look at the single thread, after all 4 sample instructions are issued, they will have values which are close by. This also means since the thread is already loading values which are close by, it can directly compute again MIP1 is always given, but also directly MIP2 without the need to communicate with any other threads. And then for MIP3 we need, in this case, local data share. We still can't use the quad swizzles because our threads are still arranged in a row major pattern and not in a quad pattern. Let's change this now. So let's recalculate our thread indices that they are not in a row major pattern anymore, but in a quad-like pattern using the algorithm I presented previously. So we have now this quad-like structure, also called Morton-like ordering. So Morton-like ordering is exactly this quad-like swizzle. Again, here to notice, well, we have now this quad-like pattern in the thread indices, but if you look at the single thread, the 4 2x2 quads are still close together, which means if you look at the single sample instructions, the data will be scattered around, but if you went to all 4 sample instructions, one single thread will have data close by. So this means that for computing MIP2, we don't need any communication between the threads because the data is already available within the single thread. And then if we go to MIP3, we need some inter-thread communication either by using local data share, so this is always possible, or now in this case we also can use quad swizzle because now our thread indices are arranged in a quad pattern. And we could try this out and then measure again if this also gives a further performance speed up, and I will do this later. And then our last texture access pattern we'll try out is, again, our thread indices are in a quad-like pattern, so in a Morton-like ordering, but now we basically distributed the 4 2x2 quads within a thread. We scatter them around so that if we have a single sample instruction, that all threads are actually loading a consecutive block of data. So again, 32 by 32 per single sample instruction. If we look at the advantages and disadvantages again, then for MIP2 now we can use quad swizzles or we use local data share, but for MIP3 we need to think about something else. So local data share always works, or we use some swizzles beyond quad swizzles, so using, for example, shuffle XOR or something like this. So shuffle XOR is a subgroup operation if you're on GLSL, but it's basically just swizzling beyond a group of 4. This would be within a group of 16. Yeah, now let's go to the interesting part about performance. So if you take the first approach I was talking about, the first approach was a row major like pattern. And then we have the last approach I talked about, which was the only change between the first and the last was that we had the thread indices recalculated into a quad-like pattern, into a morton-like ordering, and this showed a performance improvement about 8% for the specific example. So we had downsampling at texture size of 4096. We have an RGBA16 float format and generating 12 MIP levels. So if you do this downsampling, generating 12 MIPs, then about this complete pass, we see a 8% performance improvement by just changing the way how the thread indices are organized. Now the other two examples I also mentioned, so the second and the third example, they were actually slower than the last approach. So why were they slower? It's because if you look at the single sample instruction, you were actually loading scattered data, which actually reduced the cache efficiency. So this also in terms, as a result, it doesn't make sense to load more like close by data within a single thread as you can load with a single instruction. So this 2x2 is still fine because you can use sample instructions with bilinear filter, and then it's just one instruction where you load all this data. So if you look at the whole thread cube, you are loading consecutive data like neighboring pixels within a single instruction. But if you like increase this quad to 4x4, we don't have this anymore because we now need 4 single sample instructions to load actually all this data which is close by, and then you get like worse cache behavior because we have so many threads and one thread group is issuing the first sample instruction, then it has to wait, so the next thread group issues already next, and so you are really scattered access behavior. And if you don't do this, if you just stick to a 2x2 quad per thread per single instruction, and then the neighboring thread is accessing the neighboring 2x2 quad, then you have a sample instruction which is actually really accessing neighboring pixels. So, but yeah, so just be aware of that. But in general, recalculating your thread indices using a morton-like ordering does lead to better performance. It's using the caches more efficient because it's actually making use of the fact that how textures are let out in memory, and textures are let out in memory following the standard swizzle, which is following a 2x2 quad swizzle. And then of course the other nice advantage here is that we could use potentially quad operations. This obviously depends very on your specific problem case. So in case of downsampler, it's useful, and this could be another potential performance improvement which becomes available by using exactly this texture access pattern. Okay, now let's talk about workload and data distribution. And this is basically answering the question. So we loaded from the source texture using the last approach I just presented before. So we have like this morton-like ordering of the threads, and then each thread is loading 4 2x2 quads which are scattered around, so that if you look at a single sample instruction at all threads, they're actually loading a block of 32 by 32 pixels. And then we load from the source texture and compute directly the output values for MIP1. And now the question is, how do we compute MIP8? Because we need to reswizzle our data to the threads, because now each thread holds 4 output values. We need 4 output values to compute the next output value for MIP2, but we need 4 output values which are in a 2x2 pattern, and currently our threads don't hold 4 values in a 2x2 pattern, but they are scattered around. So to change that, we can use local data share and potentially also quad swizzles, but for now let's forget about quad swizzles and just use local data share. So basically each thread is storing the output values into local data share. This is an area of size 32 by 32 because our patch with the output values has exactly the size. And then each thread loads again 4 values, now in a different ordering, so that each value holds 2 by 2 quads, and then it can compute the next output value for MIP2, which is now the patch is of size 16 by 16. So if you look at the LDS, we need obviously every entry. So each thread is storing the value. Then we need to issue a barrier actually, so we need to be sure that every thread is finishing with storing, and then we can load from this local data share in this quad pattern. So I marked here the quad, so each thread is basically loading 1 quad. So obviously we need all threads, so all threads are active and they're just loading 4 values from the LDS in the quad pattern. Then they're doing the reduction, so all active threads. And then they're loading their output values again to local data share to compute the next MIP level. So this is the output value of MIP level 2, and we need to store them into LDS to do a reshuffle again so we can compute the MIP level 3. So where to store the LDS values now? So it's important that each thread stores its output value into one of the entries where it's originally loaded the values from, so we don't need any synchronization between the load and store to LDS. We only need a synchronization after the storing, but by reusing the entries where the thread just loaded the values from, we can get rid of one additional synchronization step. So obviously it doesn't matter in which entry of this quad. For simplicity, I just used here in this example always the quad entry 0, but it doesn't matter if we use the quad entry 0, 1, 2, or 3. Yeah, so for MIP2 to go down to MIP3, so MIP2 has a size of 16 by 16, MIP3 has a size of 8 by 8. This also means we have less values to compute, so we need a less amount of threads. So now we need only a 4th thread, and the other threads are inactive. So every 4th thread, we can decide this by just taking thread indexes modulo 4. If this is 0, then we take this thread, and otherwise we don't use the thread. So this leads us to a thread activity pattern like this. And if you remember well from the beginning of my talk, then yes, this looks very much like our previous example, which was the one which, if you can remember, the not really efficient one, because we have to issue all wavefronts, all lower upper parts in case we're running wavefront 64, and we can't skip anything here. So let's choose our active threads a bit smarter. So we now take just the first 64 threads, and the other threads are now inactive. So our thread activity pattern looks now like this. So all active threads are grouped together. And yes, this looks exactly like the last example we had before. So the one where we actually could skip instructions issues. And if you compare the performance again, now this example here is actually a 4K texture. So 2106 times 3840. Format is RGBA 16 float. If you downsample completely, so this should be 11 MIP levels. And by just changing the way how you choose which threads should stay active and which one can become inactive, there was an observed speed of about 7%. Yeah, and now the last part of the presentation, it's about shader optimizations. And if you can remember before, it's about how can we use DPP and or LDS per mode instructions to further speed up our downsampler code. So this is basically about how can we exchange the data between the threads. So before we were always using LDS, but as I already pointed out, since we have this quad-like texture access pattern, we actually can use quad swizzles, or even further go beyond. We can also use swizzles with like also quad-like structure, but just the delta between the threads is larger. So in a quad it would be just 1, but we could also use the delta of 2 or 4, depending what we need. And the first idea is that why don't we like to further like smaller entities. So now we look at the single wavefront and we compute a patch of 32 by 32 within this single wavefront. So this within a single wavefront, we can use European LDS permute, right? This is important. If we try to swizzle between two wavefronts, we can't use European LDS permute anymore. We need to use LDS. But if we stay within a single wavefront, we can use these instructions. So why not just stick within one single wavefront and compute as much as possible within this one, and then when we can't produce anymore, we look at a complete thread group. So in this case, this would be if we downsample a 32 by 32 patch within a single wavefront, then at the end we would have 4 values left where we need to do some synchronization between the different wavefronts within a single thread group. So of course, this idea assumes a thread group of size 64. We just learned that on IDNA we don't know, right? We don't know if a wavefront is of size 32 or 64, so this is a problem. But maybe it's not that much of a problem, because there's one important thing to notice. If you are on Vulkan and if you use subgroup operations, the wavefront size is actually fixed to 64. Well, the idea is explicitly using subgroup operations, so we know our wavefront is of size 64. Also really important to notice here is that if you're on DirectX 12, this is not true. So if you're on DirectX 12 and you're using wave operations, the wavefront size can still be either 32 or 64. So this is a Vulkan only fact. And also if you're on Vulkan and if you use subgroup operations, so yes, the wavefront size is fixed to 64 unless you use a special extension, the extension to enable variable subgroup size. So, but if you don't use this extension, then the wavefront size is fixed to 64. So in our case, just assume we are now on Vulkan, we are using subgroup operations, we don't use this extension, so we know, okay, our wavefront size is 64 and we can try out our idea. So first, from going to MIP1 to MIP2, we use quad shuffles. Quad shuffles, Vulkan, we can just use GLSL, so subgroup quad swap horizontal, subgroup quad swap vertical, and then calculating the average of it to do the reduction. And we have our output value for MIP2. So if you are using quad operations, we are hitting all the checkboxes. So because we are actually only swizzling along a group of 4, so we can use DPP. And yeah, so this is very performant. So the output values are now only in threads with the indices 0, 8, 16, 24. Like if I'm in the quad like pattern, it's 0, 4, 8, and 12. And these needs to now be swizzled again, so we can compute the next output value. So from MIP2 to MIP3, we need to swizzle between thread 0, 4, 8, 12. We can use the subgroup shuffle XOR operation for that. And we are still very fine, so we are not shuffling across a group of thread of 8 anymore, but we are still staying in this group of 16, so DP is still possible. It's still very performant, no issues about that. Then if we are now from MIP3 to 4, we need to swizzle between the threads 0, 16, 32, and 48. And now we're actually going beyond this group limit of 32. This means, but obviously we can't use DVP anymore because we are not in a group of 16, but we also can't use LDS permute because we are also exceeding this limit of 32 threads. And this is very in performance, so we can't use any of this like efficient instructions, so the compiler needs to use something else. And as I briefly already mentioned, it's using some really weird if and else branches, read first line, and yeah, it's really the code looked quite horrible when I looked at it. So, but now let's also look at the performance, and the performance wasn't stunning either. So sometimes there was actually a small performance increase, but this also could be like in some inaccuracies during the measuring process. But the bad part was that in many cases actually observed the performance drop of about 10%. So this was in total not a real improvement. Then we still have the previous stated problem that it assumes a wavefront of size 64. Not all GPUs are running a wavefront size of 64. Like even on RDNA, we don't really know if we are on DiX12, we don't know if it's wavefront of size 64. It could be also wavefront of size 32. So this is not really practical. Like performance is not better. We can only use it in limited cases, and the only really good like property of this technique is that it's really just using a small amount of LDS, so I think it's just 4x4 local data shows almost nothing, but that's the only good property and it's not really worth it. So let's rethink our idea. Let's just use the DVP LDS permute instructions for a quad swizzle. So if you go from MIP1 to MIP2, let's use the quad swizzles, and for all the other MIPs, we use local data share. So basically we just use this step. And remember, this is for a quite time-consuming MIP. So if you go from MIP1 to MIP2, the resolution is still quite high, and we save a complete step from storing and loading to the local data share. So this is a good thing. And if you look at the performance now, so this time I actually looked at not only the RGBA16 float format, but also the RGBA8 UNORM format. I looked at different resolutions, and in general I saw a performance increase, especially for low resolutions. So for low resolutions, it did benefit from these quad swizzle instructions. For high resolutions, to be honest, I didn't really saw a big difference. So you can also just say, okay, this could be just an inaccuracy in measurement. The reason probably is because for high resolutions, we are mainly bandwidth bound. So for high resolution, we need to optimize the texture access for the source image, but for low resolution, where we in general make better use of the cache, because the data just fits better in the cache, we don't have so much data to load in general, so there we can benefit from these quad swizzles. So yeah, here again, for high resolution, not so much of an improvement, but for low resolution, we do see an improvement by using the quad operations. So on average, I would say it's between 3.5%, but for lower, it's more like 5%, and for higher resolutions, it's even less. But that's not all. So this was just about the performance if you look at the single shader. But usually the shaders are in an environment, they can overlap with other shaders and stuff, and then not only the pure performance is important, but also some other properties like LDS. How much LDS is the shader using? Remember, not only like on computer shares, you are explicitly using local data share, but local data share is also used by pixel shaders. So if you're overlapping compute shaders and pixel shaders, and the compute shader is actually using local data share, then it's accessing resources which are also needed for the pixel shader. Same is for VGPRs. So VGPRs are needed by FV shader. And if you use more of them, then you have less available for other shaders which may want to run in parallel. So if you're overlapping this downsampler with other passes, it becomes very important to use as less local data share and as less VGPR as possible to increase the efficiency of this overlap. And this can obviously also affect performance at the end if you look at a complete picture and not only at a single shader. So compared with the VGPR occupancy, so we see a nice decrease in the Vulkan case, because for Vulkan it actually also increased the occupancy on DirectX 12. Not quite yet, but this can change from driver version to actually from compiler to compiler, and if you do like small tweaks and stuff. So this is for the specific driver 20.1.4. But we see the general trend when using quad operations, we have less VGPR usage. So, and this will probably stay the same. So the general trend is that we save VGPRs. Okay, now I want to briefly mention another topic which I haven't talked about in the theoretical part of the optimizations. It's 30.16, and I mentioned them here because for our specific case of the downsampler, it's actually a viable option to use 30.16 because textures are usually have only 16 bits per channel or even less, so they are perfectly suitable in just using a reduced position because the values are anyway stored in a reduced position. And then also a nice thing to note on RDNA, there's now full rate for filtering of 4-channel 30.16 textures. So this is also now really efficient in RDNA, so you are not limited by this fact anymore. Again, I did the same, similar tests for this 30.16 variant. So again, two formats, RGBA 8 UNOM and RGBA 16 float format, different resolutions, so really small ones here as well, 256 squared, and then up to the screen resolution of 1440p. And you see again, on low resolutions we see really high speed up. So to be fair, 256 squared downsampling, it doesn't take a lot of time, so we are talking here just about a few microseconds. But still, relatively, the speed up is really high. Speed up is almost zero if you increase the resolution, but so in general, for low resolutions, we see a speed up. For higher resolutions, not really, because we are still limited by the texture access of the source texture. But again, here as well, performance is not all, performance of the single shader. If you look at the whole picture, if you're overlapping the shader with other passes again, then using 13.16 has really nice properties. We are using less LES, so just half of the needed amount of LES is now used in case of 13.16, and also we could reduce the number of VGPRs needed by quite some amount. So here are the VGPRs example for the specific driver version. So if you don't use subgroup operations, so just local data share, and then once I'm compared only local data share with 30.32 compared to using 30.16, we already see a decrease in VGPR usage, the amount of VGPRs used. And then if you use additionally subgroup operations to it, we can further reduce it. So in Vulkan at the end, we only have 28 VGPRs allocated on DirectX 12 to 37. So, and this is quite nice on top of the potential performance improvements, especially for low resolutions. So this is the end of my talk. It's quite some time, so over an hour, so I hope you will stick with me until the end. But just a quick recap. So I started the talk with talking about the architecture itself, so I gave an overview, also in comparison between GCN and RDNA. And important to know is here now on RDNA we have workgroup processors, but they are pretty much like two compute units. That's why sometimes you also see the term dual compute units, and this just means a workgroup processor The only difference here is basically that on the workgroup processors, we have the double amount of scalar units and also double amount of insertion in constant cache compared to 2 compute units. Then on RDNA, we have a complete new level of cache, is the L1 cache. We have now natively wave 32. It can also run in wave 64. You don't control this is controlled by the driver. So don't assume a fixed wavefront size. As I said, since waveform v2 is now natively supported, we have single cycle instruction, and in case of waveform 64, it's dual issue. And then we also have higher geometry throughput, so we have now this automatic culling step involved. So we are still limited by 4 triangles per clock on the primitive assembler, but this also only affects already culled triangles. So for unculled triangles, we actually can go beyond this limit of 4 triangles per clock. Then for optimization, so the key takeaways are here that I really recommend if you are running a compute shader and load from a texture, do recalculate your thread indices using a Morton-like ordering so that you have this 2x2 quad Swizzle pattern, because this follows the standard Swizzle pattern and this is how the textures are actually laid out in memory. Then distribute your work to the threads such in a way that active threads are grouped together, because you can potentially skip entire wavefronts or like lower and upper parts of wavefront if you're running in 64 mode. Subgroup operations, they are a good thing. Subgroup or wave operations, they are for specific cases, of course only you can use them, but if you can, you really should consider using them. The same holds for 13.16. And yeah, this is the end. So now would be actually time for Q&A. Well, you can just send me an email instead and I will try my best to answer you. And thank you for listening to this presentation.